Let's do example 7 on page 127, and I'll read the problem. And here it is. It says 2 blocks of mass M1 and M2, with M1 being greater than M2, are placed in contact with each other on a frictionless horizontal surface, as shown in the figure, and I drew it on the paper. A constant horizontal force F is applied to M1 as shown. Find the magnitude of the acceleration of the system. And B, determine the magnitude of the contact forces between the 2 blocks. This is a very interesting problem. You see this a lot on the AP test. So here's what I've done. I'm showing the 2 masses, M1 and M2, on a frictionless horizontal plane. And the way I like to show things as being frictionless is I put wheels on. Okay, now the book doesn't do that. That's okay. And so we've got this force pushing on it. And I want to know, what is the acceleration of this system going to be? And what is the contact forces between 1 and 2? Now it said, what is the magnitude? What is the force of 1 on 2? Or what is the force of 2 on 1? They're going to be equal and opposite in direction, but they're going to have the same magnitude. So that's what we want to know. How much does 1 push on 2? So we can solve this by applying the procedure. Now, the thing about it is that if I want to know what the acceleration of the system is, notice that these 2 are in contact, and they're going to move together as one thing. So all of this mass is going to be accelerated by this one force. So what you can do is draw the free body diagram of the entire system. And so here's what I'll do. I'll just draw it like this. And here's, M1 and M2 combined into one thing. Now I'm going to follow the procedure here, okay? So what is the procedure? Well, the first thing you do is given, find, and solve with a picture, which is what I did. Step 2, draw the free body diagram. Now if I combine this, I'm going to have a force of gravity, okay, due to 1, and and then this is going to have a normal force canceling it, 1, and then we have object 2 here, force of gravity on object 2, and then we have a normal force, object 2. But hey, these 2 forces, these forces right here are really not relevant to the problem. All they're going to do is cancel out. And then we've got this outside force, F, being applied. Now, I'm going to go to the next step, which is to establish my coordinate system, XY coordinates, and break up the forces into components if I need to. I'm just going to make this the X direction, and this the Y direction. Here's a hint. If you know what direction the acceleration is in, I quite often align my axis system with the known acceleration. I know this thing's going to accelerate to the right, so I make to the right my X direction. Okay, and it's kind of obvious. Now, the nice thing about this problem is nothing needs to be broken up into XY components. These are all in the Y direction, these are in the X. Now, the next step is to apply Newton's second law. And I'm going to ignore the Y direction in this problem, because the Y direction, we don't need it. We don't need to know the normal forces, we don't need to know the weights or anything. So I'm going to say, let's sum the forces in the X direction equals MA in the X direction. Okay, now we're going to do it. We're going to add up all the forces in the X direction. Well, there's only one. F. Okay, equals M. Now what is the mass? Well, it's the combination of these masses. It's M1 plus M2. This right here, listen, When you set it up like this, this is the mass of the free body, the entire free body. A mistake that some students will make is, yeah, but the force is only contacting M1. Doesn't matter. This force is accelerating the system. So you have to include the mass of the entire system. Okay, so this is the mass of the system that is accelerating, and times A. And now I do step 5, which is just solve for the unknown. We want to know what the acceleration is, so I solve for it. Acceleration is just going to be the force that got applied here divided by the total mass. And this is my answer. Now, it does bother some students to have problems like this where there are no numbers. Get used to it. The higher you go in physics and math, the fewer numbers you use. Okay, because at some point they're going to realize, oh, people already know, but we're going to assume you guys know how to use a calculator. What we want to know is, can you derive expressions to solve problems? So this was all for part A. Now let's do part B. We want to know what the contact force is between these. So here's one. I can do it one of two ways. I could draw a free body diagram of object 1, or I can draw a free body diagram of just object 2 to get that contact force. Either way you want to do it, it's fine. I'll do it the hard way. I'll draw a free body diagram of object 1. So here's object 1, M1, and of course we've got gravity pulling it down. I've got the normal force supporting that weight, so that leaves no acceleration in the y direction. And I've got F like this. But now I've got another force, right? M1 is pushing on M2, therefore M2 pushes back with an equal and opposite force. So this is the force of object 2 acting on object 1. And it's going to be in the opposite direction. Does that make sense to you? Look at that picture. And raise your hand if that does not make sense to you. Okay? Or give me a signal. Give me a sign. Okay? Okay, so object 1 has to push on object 2. And here's what I can do. I can actually, you know what I'll do? I'll draw those interactions right here on this free body. See this free body diagram? Here's object 1 pushing on object 2. This is the force of 1 on 2. But object 2 pushes with an equal and opposite force on object 1, force of 2 on 1. These forces of 2 on 1 and 1 on 2 are internal to this free body diagram, so we didn't include them in the free body diagram. They just cancel each other out. But if I'm just drawing a free body diagram of object 1, I have to include it. If I'm only drawing a free body diagram of object 1, the force that 2 applies to 1 is now external to the free body diagram. It's an external force and must be included. So now I'm going to, again, ignore the y direction. Let's just sum the forces in the x direction equals ma in the x direction. Notice I do the same thing all the time, same routine, same procedure. Okay, so now I'm going to sum the forces in the x direction. I've got F, and then minus the force of 2 on 1. Why the minus? Because it's going to the left. I could put plus negative F2 on 1, but, and so then this is going to be equal to M1. Like this is just M1. It's not M1 plus M2. It's just M1. Because that's what my free body diagram is. And then times A. So this lets me solve for the force of 2 on 1. So let's do that. This is, whoops. I don't think I have much eraser left there. This is M1 times A minus F equals, oh, negative. So I got to switch that. So the force of 2 on 1 equals, oh, doggone it, equals F minus M1A. But I know what A is. A is this. So this is going to get kind of messy. This is going to be F minus M1 times A, which is F over M1 plus M2. And so this is going to let me let's see, what did yeah, no, that's right. So the force that 2 applies to 1, the contact force between these guys, is going to be equal to F times 1 minus M1 over M1 plus M2. And let's see. Now there's another way we could have done this. I'm still on screen here. This was the harder way. I'm going to just take a look at M2. Draw a free body diagram of M2. So here's the alternative solution to B. Oh, I know what I'll do. Just tilt the camera. Here's M2. And here is the force I want. This is the force that 1 applies to 2. The contact force of object 1 on object 2. And then this is the normal force and the force of gravity, M2 times G. But these two just cancel each other. And so now if I sum the forces in the x direction equals MA in the x direction, I've got F1 on 2 is equal to M2 times A. But what is A? A is F over M1 plus M2. And so F1 on 2 equals, oops, oh gosh, come on. F1 on 2 equals the force times the ratio, or times M2 over M1 plus M2. Now, this was my answer doing it one way by choosing M1 as my free body diagram, or as my free body. Are these two forces the same? These don't look equal, do they? Well, let's manipulate this a little bit. F times, well, I'm going to say this is M1 plus M2 over M1 plus M2. Right, I can do that. I'm just putting a common denominator there. Minus M1 over M1 plus M2. Y'all see what I did there? I'm just taking this, say here's 1. Well, 1 can be written this way. I'm going to add these, or subtract these actually, and I need a common denominator to do that. Well, what is M1 plus M2 minus M1? Well, M1 minus M1 is 0, and then I just add M2 to 0, and I get M2. And you can see that these two answers really are equal if I just simplify this a little bit. So there you go. And that's how you use the, I don't know if I can get this all in one. The whole thing here. But here is example 7. Oops. So, and the thing is that you can draw things as a single free body diagram if it's all connected together. And then you can look at the constituent parts of that system, draw the free body diagram of those constituent parts, and figure out forces that were internal to the big thing. Anyway, any questions? Okay, that is all.